Record. Okay, so today we shall discuss the method of Aryabhata for solving equations of this type ax plus b equal to cy plus d. So here a, b, c, d are positive integers and we want to solve this and find out integer solutions x and y. So how this is done, that is what is mentioned in the last two verses of Aryabhata. So verse number 32 and 33, these are the last two verses of Aryabhata, Ganitapada. And then that is the end of it, and then he starts with some other topics. So I will just read this. Adhikagra bhagaharam chindyat unagra bhagaharena शेष परस्पर भक्तम मतिगुणम अग्रांतरे क्षिप्तम अध उपरि गुणितम अंत्ययुग उनाग्रच्छेद भाजिते शेषम अधिकाग्रच्छेद गुणम द्विच्छेदाग्रम अधिकाग्रयुतम. So the meaning of this will be again clear by examples, but still at least we try to see what is there in this in short. So a and b, these are the positive integers, or b can be 0. So these are the numbers in this expression ax plus b, and you want to find out a number capital N such that when you divide by that number by a, you get the remainder b. And if you divide that number n by c, then the remainder is d. So in other words, capital N should be equal to ax plus b, and it should also be equal to cy plus d. So b and d are remainders, therefore they are respectively smaller than a and c. Now the method is explained here, what you should do. So this b and d, they are remainders and they are called as agra. So b is agra and d is another agra. So you consider adhikagra bhagaharam. Adhikagra, now b and d, suppose b is 4 and d is 2, then b is larger. So whichever is larger, adhika. So adhika agra means the larger remainder. So that larger remainder you consider. So now a is a divisor actually corresponding to the larger remainder. So bhagaharam means divisor which corresponds to the adhikagra. So divisor which leaves larger remainder. So that is a. So that you consider, and that divisor you should chindyat, means you should divide that thing. So a should be divided. So you see that a should be divided by what? C. C is this here. C is also a divisor. Means you are dividing n by c and finding the remainder d. So c is a divisor corresponding to the smaller remainder d. So you should divide. So take this c and divide this a by c. So again let us see. A is adhikagra bhagaharam, means b is larger than d is considered here. A is the divisor corresponding to the larger remainder, and c is the divisor corresponding to smaller remainder. And what we should do is the divisor a which corresponds to adhikagra, that should be divided by una. Una means less, smaller agra bhag agra. Unagra means smaller agra, that is smaller remainder. So the corresponding to that, what is the bhagahara means divisor. So the one by which we are dividing. So that is actually c. So you should divide that by the divisor which leaves smaller remainder. So this is a starting point. Now once you divide a by c, then there will be some remainder. So by that remainder you divide c. So this is the procedure which Aryabhata describes as paraspara bhaktam. So you divide one by the other and go on doing like this and reach the final remainder. So Shesh, or you also in this method of Aryabhata, you can stop in the in between also, provided the number of divisions is an even number. So the number of labdhi is actually division and final answer that you get. So quotient that you get, that is labdhi, and the number of these is actually even number. So this even number is not clearly mentioned here, but that is what is understood by using the commentaries of other mathematicians such as Bhaskar 1. So you should go on dividing and you stop somewhere when you finish even number of divisions. There is also a small correction to that. That correction is that the initial division A is divided by C. This division is not to be counted. And after that, you count the number of divisions that you are actually doing. Now, once you get the final remainder, final means you stop at some stage, say even number of steps, and at that time you get some remainder. So that remainder, mati gunam. So shesha you means remainder, mati gunam. Now mati is something which is to be found out by your mental exercise. You can say that you should find out mati. Now that mati is to be found out. So multiply this remainder by mati. Let us say z, some number z. Now after that, after multiplication, you add b minus a. B minus a is what? B is agra and D is also agra. That is, both are remainders. Now agra antara. Agra antara means difference between the agras or difference between the remainders. So B and D are remainders and their difference is B minus D. B minus D. So I have written B minus A, but it should be B minus D. So multiply the final remainder by mati and add B minus D to that. So this is what is to be done, and this should be divisible. Now the condition is that this should be divisible by the final divisor is there. So when you do the one another division, then there is final remainder and final divisor. So final remainder into mati plus b minus d, that should be divisible by the bhajaka, that is the divisor, last divisor. So this will be more clear when you do the problem. And then there should not be any new remainder. So the expression is completely divisible by the last divisor. Okay. Now after that there is a procedure. So at least maybe first of all I will explain this part by an example, and
Sir.
then it will be better.
Sir, excuse me.
Yes.
In the first step,
Yeah.
now B is greater than D, and we
Yes,
divide by A C. We divide C by A.
Yeah. So when this B is bigger than D, you are dividing this A. A means in this example
A by
34 by 30. That's what we are doing.
A by C, but C may be greater than A.
That is possible. So C may be bigger than A, but still you divide as a formality.
So that first you get divisor 0.
That will be 0. And you are not counting that.
Yes. And now since D is smaller, you divide B by D. Or
so now in this case, now B is, you are only saying B is 2 and D is 1.
Okay.
So B is bigger than D, that is to be used. And the corresponding thing, which may be 13 as you are saying. Suppose it is 13x plus 2 is equal to 34y plus 1. This may be the case. Then you divide 13 by 34 formally. You will get quotient as 0. And then the remainder In that case, you are dividing 13. So the remainder will be 13. So that after that, you are dividing this 13. Yes. So you can carry out that if possible. That so 13 is there. Yes, that's right. 13 will be the remainder in that case. And then you have to divide again 13. That is, remainder should divide the divisor. That means 13 should divide 34. That is true. So 34 is divided by 13, and then this 2 is the quotient and so on. That is how we should proceed. Yes. So this is how we have to proceed in that case. And the first quotient is to be discarded in that case. Now, in this case, when 34 is divided by 13, in this example that I am explaining, 34x plus 2 is equal to 13y plus 1. So divide 34 by 13 and remainder is 8. Then by this remainder you should divide 13 and proceed. So 13 is divided by 8, then there is 1 as quotient and 5 is the remainder. Then this remainder will be dividing the divisor 8, and you can get 3 and so on. And go on dividing, and you can stop whenever there are even number of divisors. So here there are even number of divisors. You can stop here, or you can go ahead and finally here you are getting 1 as the remainder, and number of divisions is even here also. So this is 4 division case when you stop here, and in this example there is also 2 division case, means if you stop here itself, when you get 3 as the remainder, you have done 2 divisions apart from the basic division. So in both there are these 2 possibilities, and any of them is okay. So this is what is explained in this, that Shesha Paraspara Bhaktam. Then after that, this calculation is to be done. That final remainder you should look at, multiplied by Mati and add b minus a to it. And Shiptam means you add that. Okay, so this is what calculation you have to do. And in this example, you should okay, so here Mati to be found out, remainder in this case is 1, final remainder is 1, and final divisor is 2. So what is Agrantara? Agrantara is 2 minus 1. Agra is 2 is Agra and 1 is another Agra. That is their remainders, initial remainders. Their difference is 2 minus 1. So I am taking Mati to be 1, and this 1 is written over here. This remainder, final remainder is written over here. Mati is 1. If you take Mati to be 1, then your problem is, this problem is solved, because 1 into 1 plus 2 minus 1. That is 2, and it is divisible by this 2. This 2 is the final divisor. So final divisor can divide this expression if we take Mati equal to 1. And Mati can have more values also. Like Mati can be 3, Mati can be 5 and so on. But Mati cannot be 2, or it cannot be an even number. So you should find out some Mati which satisfies this equation. That is, equation means this expression is divisible by this final divisor 2. So then you find out the quotient. That final quotient is 1. Q equal to 1. That let us call that as Q. So far the calculation is you have found out Mati You have found out these four divisors. All the four divisors you have found out. Then you have found out Mati, and you have found out this final Q quotient. When the expression Mati into Baki, remainder, plus Agrantar, you divide that by the final quotient and get the new quotient Q, which is equal to 1. So once you do this, you have to make a sequence. So let me go back. Now you make a sequence or Valli, it is called Valli. So Adha Upadi Gunitam Antyayuk. So this is what I am writing A into B plus C. So in the sequence, what you have to do is two numbers one below the other, you should multiply them, A into B, and then add something below that, that is suppose C, you should add that to that. And so here what you should do is, you should first write down the four quotients, 1, 1, 1, 1. They are the four quotients, 1, 1, 1, 1. After that you write Mati, and then you write Q, that is the quotient. So you get a sequence. In this sequence, you have to do this calculation 1 into 1 plus 1, A into B plus C. So here A into B, 1 into 1 is 1, plus 1 is 2. So that 2 you should write here. Means you should replace this 1 by 2. So I could have wiped out this 1 and I could have written this 2. But for convenience, I am writing this 2 here separately. Then below that, I am writing this Mati. And this 1 is now of no use now. We have already used it. So we have get 2 and 1 now. Instead of these three numbers, I am getting two numbers, 2 and 1. And after that, this 1 you should keep here. So this is a new triple, 1, 2, 1. But for the new triple, again, you should use the same rule, A into B plus C. So 1 into 2 is 2, 2 plus 1 is 3. So we are getting the number 3 here. Now, this 3 and this 2 as it is, so these two numbers we have got. The third number you should not consider. You can wipe it out if you like. And next one you should take from the top here. This one is taken. So 1, 3, 2. This is the new triple that we have got. Once you get the new triple, you can use the rule A into B plus C. So 1 into 3 plus 2, that is 5. Okay, 3 plus 2 is 5. Now below the 5, you should write this number 3 and you should wipe out this 2 is not required now. And now take the new 1 there. So 1, 5 and 3. So A, B, C. A into B plus C. So 1 into 5 is 5. 5 plus 3 is 8. So you get 8 here. And this 5 you may write here if you like. Now this 8 is an important number. And this number, last number 8, is actually the value of X in the original problem. X is equal to 8. But Aryabhata has given a, if you want smaller answer, then what you should do, that is mentioned by Aryabhata. So let us go back to what Aryabhata says. So you do this procedure of AB plus C and get something at the end. Now that should be divided by C. This C is here. C is corresponding to D. What is D? D is unagra. Una means smaller agra or smaller remainder. So something corresponding to smaller remainder is C. So unagra cheda bhajite. So unagra cheda. So the divisor which corresponds to unagra, that is C. So you divide the answer what you have obtained, that is X, you have obtained by C. and then whatever remainder you consider, so that remainder is to be called as x. In our language, what is the value of x? So I said that first of all, you can get the last number, that is 8. But if it is large, you can further simplify it by dividing by c. Divide by c and find the remainder, and that is the actual value of x. So in this problem, here 8 is there, and what is c? C is 13. But our number 8 is already smaller than 13, so you don't have to divide. But suppose instead of 8, you would have obtained 21. Then you would have divided by 13 and you would have got the remainder as 8. So the idea is to get a small solution, x. And this is how you get the small solution that is mentioned by Aryabhata. So once you get this x, how to get the number? So that x to be multiplied by 34 and then you add 2 to that, that gives you the number n. So that is the method. So what Aryabhata says is, because it is not written in terms of variable, arithmetic. So what is said here is adhika agra cheda gunam. So this 34x plus 2, that was the thing. So adhikagra, that is ax plus b, that b is there, which is larger. Corresponding to that, there is a. So multiply by a. And what is to be multiplied by a? Dvicheda agram. Means in your sequence, last two numbers are there. In our example, they were 8 and 5. So last two numbers, 8 and 5 are there. Out of them, the first one, that is 8 is the first one, 5 is the second one. That you should consider. And multiplied by a, and then adhikagra yutam. So add b to that. So ax plus b. What it says is that these last two numbers are there. Out of them, you take this a, multiply this by a. This is a 34, and add adhikagra 2 to that, and that is the answer n. And if you want to find out why, you can find out from this. But idea was to find out the number n which leaves remainder 2 when divided by 34, and which leaves remainder 1 when divided by 30. So that number n we have found out by this method. So you see that Aryabhata explains the things, but not completely. One has to understand some steps in between. And so let me just read it. Divide the divisor which gives greater agra by the divisor which gives smaller agra. This division is not counted. The remainder is reciprocally divided. That is, the new remainder becomes the divisor of the original divisor. This is like the GCD algorithm. Now the remainder of this division becomes the divisor of the second divisor, and so on. So the number of divisions carried out should be even. Carry out divisions till the remainder and divisor are small. So this is an explanation that you can, where you should stop. So you should stop at even number of divisions and even number of divisions. But when the divisors and remainder are small, at that place you can stop. Okay, now forming the chain. The quotients in these divisions are placed one below the other in a chain, which is called as Valli in the old literature. The last remainder is multiplied by assumed number Mati. So Mati into remainder. So that this product, when added to Agrantar is b minus d. So that is divisible by the last divisor. That is the requirement. Let the quotient be q. In the chain, put at the end Mati. That is, You are listing the quotients. At the end of all these quotients, you put Mati, and below that you put Q. That is the final quotient that you have obtained. Now use the AB plus C rule. If the last three numbers in the chain are A, B and C, then replace A by AB plus C and remove C. Take last three numbers in the chain as A, B and C and continue till only two numbers remain. The last A is divided by small c in the equation. Small c corresponds to the smaller agra. The remainder is the value of x. Now, this last division divided by c is made to make x small. So this is the method. So I have explained this by one example here. N equal to 35 plus 2 is equal to 13y plus 1. Okay. Now, if I had taken only two divisions in this, only first two divisions suppose, then what is the final remainder is 3 and final quotient is 5. So these numbers are important. Now what is the method? Mati into final remainder, this is 3, plus agrantara. Agrantara is 2 minus 1, that is 1. That should be divisible by 5. 5 means this second divisor. And now, if I take Mati equal to 3, then I can do that. 3 into 3 plus 1 is 10. 10 is divisible by 5, and I should find out the quotient. So that quotient is equal to 2. 2 is equal to 2. So now my sequence, what is my sequence now? There are two quotients because only two things were taken. They are this one, and this one. These two quotients are there, which I have listed one below the other, 1 and 1. Below that I should write Mati, that is 3, and below that I should write 2. So 1, 1, 3, 2 is my new sequence. So once this sequence is formed, I should use AB plus C rule. And that rule gives me 1, 3, 2. In this 1, 3, 2, 1 into 3 plus 2, that is 5. And now this 5, 1, 5 and 3. So 1 into 5 plus 3 is 8. So I have written 8 here directly. So 8, 5 is are the last two numbers, and 8 is the top number, which is the value of x. Because you could have divided by 13, but it is not necessary. So x is equal to 8. And from that you get the value of n. So if you stop after two divisions also, that is no problem. So this is Q is here. So Q is obtained in the following way. Mati is here 3 multiplied by this 3. 3 is last means this remainder. So Mati into Baki, remainder, plus Agrantara, this expression you calculate. This is 10. That should be divisible by 5 is our requirement. 5 means last divisor. Now, once you actually divide, you get the quotient, and that quotient is Q. Yeah. So it should be divisible, and you actually find the quotient, and that is in the sequence, that quotient Q is the last number. So 2 is the last here in this sequence. So then your calculation AB plus C starts from that step, and you can go ahead with that. So this is one example. So one more example we can do here. Now in this example, I have taken one remainder as 0. So you see 100x plus 1 is equal to 63y plus 0. Now again, Agrantara is 1 minus 0, and that is 1. And 1 is bigger than 0, that all that is there. Now the question is to solve this equation and find n. Find n such that when you divide n by 100, then the remainder is 1, and divide by 63, then the remainder is 0. Now, if you solve this, what is the advantage? So the advantage here that I want to point out is that modulo 100, you get 1 is equal to 63 into y. 1 is equal to 63 into y. So you have got the inverse of 63 modulo 100. That is the advantage. By this method, you are getting the inverse. And usually, we do, you would have observed that finding inverse is done by Euclid's algorithm, and you try to write GCD as a combination. GCD is 1, which is a combination of the given numbers. So this is exactly what we are doing here. But the method is actually told in terms of numbers, and you should follow these steps and you will get the answer. That's what is mentioned here. So let us. No. It is not there. Here actually, even number of steps that is used to save the number calculations. Okay. So you can stop anywhere is the idea. So what is happening is you are reducing the given equation. If you try to give a proof of this, you will find that you are reducing the original equation to a simpler equation of the same type, which you are able to solve orally. That is the idea. Because if you see this equation, Mati into Baki, you see previous equation, that Mati is to be found out, Z. So 3 into 3, that is this last thing, plus 1 is divisible by, so plus 1 is 2 minus 1. 2 minus 1, that is this 2 as well as 1, this is taken care of, both the remainders. Okay, 2 minus 1. And you are able to solve this equation, 3z times something plus 1 is divisible by this 5. So this 13 now is replaced by 5 and y is found out as q. Okay, y is found out as q. You are able to solve this simpler equation in which we are doing, and you are finding the value of y actually, which we are calling as q. So wherever the numbers are small, you can stop there. That is the idea. You don't have to go up to the end. Whereas now this is not a completely computer algorithm. This is a computer algorithm, but at the end you are using your wisdom and you are stopping at the appropriate place. But what Bhaskaracharya has done is Bhaskaracharya has actually considered a computer algorithm. So because of that, he has to make cases. So he makes the cases like this. What happens if you stop at even number of steps? Stop means you are going up to 1 now. Especially when the GCD is 1, GCD of the given numbers is 1, then at the end you will get the number 1. Otherwise, you will get GCD, whatever it is, maybe you are getting 2. But what Bhaskaracharya does is that he says that if it is 2, suppose the GCD of the given numbers is 2, then it means that Agrantara should be divisible by that 2. Right? Because suppose 32 is there and 13 is replaced by say 14 in this example. Then because these two numbers are divisible by 2, then the Agrantara should be divisible by 2. Then you go on, why you are going ahead with that? You divide by 2 that equation. That's what he says essentially. And then you proceed. So that your numbers will be smaller. It will be easier to do the calculations. So ultimately in the Bhaskaracharya method, you are getting 1 only at the end. That is GCD. So,
sir, this is Bhaskaracharya second.
Bhaskaracharya second, not Bhaskaracharya 1. Bhaskaracharya 1 only explains what the method of Aryabhata is explained by him. Or to say it more exactly, I have not seen what exactly Bhaskara 1 has done, but I have seen what Bhaskara 2 has done. And he actually makes 4 cases. 4 cases means this 2 is bigger than 1, then 1 is bigger than 2. I mean, suppose it is 34x plus 1 is equal to 13y plus 2. All these different cases he does separately. So means that instead of +2, it is -2, for example. So in different ways it can be said. But these cases are dealt with separately, and he makes 4 cases. Now, this is like a computer algorithm. So you don't have to solve in between. Whatever it is at the end, you just use the formula of Bhaskaracharya and complete it. And computer can do it for you. So these 4 cases are there, etc. You do not understand, because when you use Euclid's algorithm, you are going at the end and you are doing calculations backward. But in those calculations, you are not using only numbers. You are also using the variables. Means you are using the previous numbers and doing calculations completely, simplifying and so on. So that we do not really understand what is happening. But then if you only want to use this AB plus C method, then you have to make these 4 cases and do it.
Sir, if I am not mistaken, Bhaskaracharya second gives a method when both x and y can be positive.
See, x and y, they are actually, I mean, n is divided by, say, in this case, 34, and then you are getting a quotient. So that quotient is positive, right? These are quotients, so they are positive. Quotient negative is not considered. You can manipulate it now. You can do that if you like. But the numbers are basically positive. But if you want to solve, now negative numbers are there. So I think he's also using negative number. 34x plus -2, for example. Such thing also he considers. But x and y are positive there. Yeah. But you can modify all these methods. Only thing, so only difference that I want to tell you is that Aryabhata tells you what happens when the number of quotients divisions is even, and Bhaskaracharya does it in a more general way by making 3-4 cases. No, be less than, then also you can do it, because if this is suppose 1 and this is 2, okay, then this you call as 34x plus means that you can call as ax plus b. Whatever is larger, that you call as b. Okay, that is the idea. This is our way of looking at it. So that doesn't matter. What Aryabhata says is that whatever is larger, you consider that, and so on. He expresses it in that way. But because we are writing using x and y, he has some difficulty. What he says is that divisor which leaves larger remainder. So you consider that part which gives you larger remainder. Okay. Now what we have done is that part we have called as ax plus b. B is larger. Okay. So these giving the names is up to you. Properly you can give the names. So only thing is that, as Barvesar has asked, that suppose it is 13x plus 2 is equal to 34y plus 1, then what you should do? But then by this method, you should divide 13 by 34. It is unnecessary, but you can do that step. Okay. So now, if you solve this, now let us just go through this for a revision. So divide 13 by 63 and you get remainder as 37. Now this 37 divides 63 and get the remainder here. So then 37 is divided by this remainder 26. Get quotient 1, then quotient 2, quotient 2 again. So these are 4 divisions. Now this is first division, 63 divided by 37, quotient is 1. So we will make a list of these quotients 1, 1, 2, and 2. Now you have to find out Mati. So Mati is such that Mati into this Baki is 3, 1 into 3 is 3, plus Agrantara is 1. So Mati into this, so 3 plus 1, that is 4, and it should be divisible by this 4. Last divisor is 4. It should be divisible by 4. So if I take Mati equal to 1, then yes, this is divisible by 4. 4 is divisible by 4. I get the quotient Q, which is equal to 1. So that Q you should be writing at the end. So Mati is 1 and Q is 1. So 1 and 1. So now my sequence is 1, 1, 2, 2, and 1, 1. 1, 1, 2, 2, 1, 1. Now you use the AB plus C rule. So 2, 1, 1. 2 into 1 plus 1 is 3. So now I use this 2, 3, 1. 2, 3, 1. And then 2 into 3 plus 1 is 7. So I write AB plus C against A. A was 2. So my sequence is now 7, 3. But I take this 1 from this. So 1, 7, 1, 7, 3. Now 1, 7, 3. 1 into 7 plus 3, that becomes 10. So 10 and 7, and this 1 I take now. So 1, 10, 7 is my new sequence. Triple. 1, 10, 7. So 1 into 10 plus 7 is 17. And there I stop. This is the value of x. Actually, I should divide this by small c. Small c is 63, but that is not necessary because this is already small number. So I stop there and I have the value of x. X is here obtained, and once you get x, you can find the value of y. So y is in this case 27, and 27, 63 into 27 is 1 mod 100, as we see. So this is the inverse. So the point is that solving this indeterminate equation is a term we use many times because there are two variables and only one equation is given. So in that case, and you want integer solutions, so the solution can be obtained, and that gives the inverse mod n. So in the new language of modular arithmetic, we have found the inverse, and finding inverse is an important step here, an important application, and we can use it in online banking. This finding the method, this finding this inverse by Kuttaka method. This method is called Kuttaka method. So in online banking, what happens is, let me, do I get, so I think I can use it. So the method here is you take primes P and Q, and these are primes which are very large, and you find out capital N, which is a product of these two numbers P and Q, and then given a message which is a number, say A, which is a number which is taken less than this capital N. So P and Q are 100-digit numbers, for example. So this is a 200-digit number, and your message string can be taken as smaller than N. And if it is larger, then you break it into pieces so that each piece is smaller than N. So once you take this message, you convert it into an encrypted message. So B is equal to A raised to K, where this is equal to means we are doing it, making it congruent to A raised to K mod capital N. So mod N. Mod N. So this B is the secret message. Now in this case, this K is chosen actually initially. So K should be co-prime to phi of N. So K is coprime to phi of n. Phi of n here is, if n is P into Q, then phi of n is P minus 1 into Q minus 1. Because P and Q are primes, so phi of n can be obtained in this way. Now, once you get this secret message, how to get the original message A, that is the question. So A is actually equal to, one can prove this, that B raised to K1, a number K1, where K1 is obtained. So this is, A is B raised to K1 mod n. And how to get K1? So K1 is obtained such that K1 is congruent to 1 modulo phi of n. Phi of n. Phi of n means P minus 1 into Q minus 1. So finding out this inverse K1 you can do by Kuttaka method. So this calculation of finding the inverse, which is required in, this is RSA cryptography, as we know, RSA cryptography. Which was explained by Rivest, Shamir and Edelman in this way. They have found out this method which is used in online banking nowadays. So Kuttaka is useful in this, and actually the algorithm must be equivalent to this Kuttaka algorithm. Now there is another method which also required here. So you see that when you do encryption, you have B equal to A raised to K, and when you do decryption, you are having A is equal to B raised to K1. So this is powering. And for powering, K and K1 are very large numbers. They can be large. So to get this very large powers of A and B, we are using the method which is called as repeated squaring method. But actually we should call this as the method of at least Bhaskaracharya. Or before Bhaskaracharya, Pingala has explained this method. And how this method is used? So let me see if this moves. Yes. So what is done here is that suppose I want to find out 40th power, then you divide 40 by 2, you get 20, divide this by 2, you get 10. So even numbers you are dividing by 10, but if you get an odd number, this is odd, so this is even, you divide by 2. This you divide by, instead of dividing, you subtract 1, so you get 4. Then 2, divide by 2 and you get 1, then you stop. So Bhaskaracharya mentions that if you want to get powers, so A raised to 1, you square, you get A raised to 2. Now you square, you get A raised to 4. Now you multiply by A, so you get A raised to 5. Now you multiply, now square it, you get A raised to 10. Then square it and square it, A raised to 40. So Bhaskaracharya calls it as Guna Varga method. Guna means you multiply by that number. Varga means you take the square. So Guna Varga. So by this way, you can very easily find out, and number of steps is much small. Number of steps is much small, and this calculation I had done. So suppose I want to find out a power k, which is a 100-digit number. Now a raised to a 100-digit number. How many calculations are required to make this multiplication and getting the power? So if I use the method of Bhaskaracharya, then only 664 or less number of multiplications. And this is why this powering can be done in a very small amount of time. So what happens is when you do powering, usually if I take square or fourth power, the numbers are becoming very large. But because in our RSA cryptography, you are interested in a raised to k modulo capital N. So you don't want the actual value. You are interested in a raised to k modulo capital N. Therefore, every time when you do a power, say square, you immediately reduce mod n. Again, take square, immediately reduce mod n. So every time your numbers are smaller than capital N. And therefore, although by squaring, the numbers become large and large, and you think that only 664 multiplications, and you may think that you are multiplying very large number. That is not the case. Because every time in this application, you are requiring answer modulo capital N. Therefore, this method actually is very useful. And this is a computer method, because you just tell the computer that now, first of all, whatever number you have, very large number, you go on dividing by 2 or subtract 1 from that and get this sequence. Then you go in the opposite direction and get the powers every time you reduce mod n. So this is a computer algorithm that a layman can actually follow this and get the answer. So these two methods, that is Kuttaka method as well as the Bhaskaracharya's or Pingala's Gunavarga method, both these methods are very useful. They are actually used. The only thing is we do not know that Bhaskaracharya had already said this. And where he has said this is also very interesting, that when you have this formula for geometric progression, so AR square, etc. And suppose I have ultimately A into R raised to n minus 1. So there are n terms in this geometric progression. Then what is the answer? So the answer is sum of these n terms is equal to A into R raised to n minus 1 upon R minus 1. So Bhaskaracharya wanted to give this formula. So at that time, Bhaskaracharya says that here you are asked to find out first of all R raised to n, a power of R. But if n is large, how will you find out this? So for this he gives this method. So first of all you find out, he says, R raised to n. After finding R raised to n by this method, then you subtract 1 from that and then divide by R minus 1. And then finally you multiply by the first term. So A into R raised to n minus 1 upon R minus 1. So when he gave this formula there itself, so it is interesting that when we teach this method of finding sum of n terms of a geometric progression, we never thought of this possibility of n large and how to do the computations. But he first explains that and then he proceeds with this formula and he explains how to find out the sum of first n terms of a geometric progression. So nowadays the government is for this AKS and so on, and this IKS, Indian Knowledge System, IKS. So these are the things which we have already done long back, but we do not know that these we have done already. Yes, we only know this repeated squaring method, but there also only squaring is mentioned, that multiplication is not mentioned. Multiply by a. But Bhaskaracharya mentions Guna Varga, so he mentions both Guna Varga method in that sense. So such innovative ideas are already there in the work of these ancient mathematicians. So with this, I will be now stopping, and I have completed the Ganitapada of Aryabhata. There are more sections in this. There are actually pada means 1/4 in some sense. Means there are 4 parts of the book, out of which Ganitapada is 1/4. 1/4 is not equally 1/4, but these are the parts, volume 1, volume 2, volume 3, like that. Now there are some other parts which are now Gitika is there. So Barvesar will be giving talks on Gitika. It has only 10 verses. And before Barvesar, Solapurkar sir will give some talks on Madhava's methods and Madhava's results. So next Monday, the lecture will be by Solapurkar sir, and he will be talking about the work of Madhavacharya. So we stop here today. Yes.
One question.
Yes, please.
You said that it can be used in these cryptography thing. Are these methods used actually?
Yes, they are certainly used, but they are not saying that these are your methods. They are saying they are our methods. That is the only difference. Because, as I have said that, so when you write a computer algorithm, you have to do like this only. There is no way. Now, in numerical analysis, it is there are shortcut methods which people have found out, because when you have to do actual calculations, you have to go into this computational, and then you have to find out these short methods, and you have to use them. If you do not use, then somebody else will write a better program than you, and then he will become famous. So you have to, use these short methods. So people have, of course, they are certainly using these methods, and they have name also. In numerical analysis, we learn this method as a repeated squaring method. That's why I told you modern name also. So it is certainly used.
That is related with binary expansion. This is related with binary expansion of 40.
This method which is given by Bhaskaracharya, finding 40th power that I have mentioned, it is inside that binary expansion of a number is there. So you are dividing by 2, every time. So you are having the highest power of 2 that is possible there. So basically, if you see it carefully, you will see that you are writing 40 as a sum of powers of 2. So 2 raised to 5 is, so basically you are writing 40 as 32 plus 8. That is, it is 2 raised to 5 plus 2 raised to 3. And that's why at this stage, you will see that there is a multiplication in between by 8. But otherwise, you are going, see, from 1 to 2 raised to 5, you are just multiplying by 2. But in between, you have to multiply by, you are squaring every time. 5 times you are squaring. But because of this 2 raised to 3 in between, you have to multiply by a. So this is kind of Horner scheme. Horner scheme is used for polynomials, finding out polynomials. So the same idea is used. So already Horner scheme is also there in the method of yes, Jadhav sir, we shall come to you also. So in the Horner scheme, that for example, you are having you want to find out this polynomial 1 plus 2x plus 3x square plus 4x cube. You have to calculate this. Then what you do is 1 plus x into 2 plus 3 into x plus, so 3 3 into, so this is already, no, x into 3 plus 4x. Yeah, like this. So 1 plus 2x plus 3x square plus 4x cube. So this is Horner scheme. So basically here the Horner scheme is used in the method of Bhaskaracharya together with powering. So that way it is a combination of these techniques. Taro sir, what do you want to ask?
Sir, chat box, some messages are there, sir.
Yes?
In the chat box, there are some messages.
Oh, I see. Okay. So chat box जरा खोलो.
Yes, sir, I may be going early.
Yeah. I
So,
will
no,
say
no.
now,
So,
lecture is
I
over.
want to welcome Chaitanya Tappu,
Okay, yes.
who is a medalist in
Yes. I
2014.
certainly
Yeah.
remember. Yes. So, yeah, what you are saying is right. RSA is a deterministic encryption algorithm, so it is generally considered less safe than probabilistic algorithms. So usually RSA methods are paired with some probabilistic algorithms or completely different encryption. That is right. So yes, so that is the general remark that you have made about these, whether to use RSA or not. All these questions are certainly there. So what I want to say is that if you want to use RSA exactly, what are the competitions involved, and how Indian mathematics is useful there. But your comment is right that certainly people are not, happy with this RSA completely because of various reasons. And now elliptic curve cryptography is also used, and some other methods. Those who think that RSA is not safe, they are coupling with some other algorithms also. So that is true, certainly.
Sorry, I should say the correct word is randomized algorithms. I blanked on it when I wrote the comment, but yeah.
Yeah, that's right. So primes also are obtained randomly and many other. So we are not going to that. But at least if you want to do these two things anywhere, then certainly our methods are useful. So cryptography developed a lot now, and as I understand, government is also not using RSA for the same reason, because one is not sure about these things. But still, I think many modifications are being done in the usual RSA, main RSA. Yes. So thank you for your comment. Yes.